This rack of 4 Jakiper batteries did really well this past week as I tested it. I went through several tests and talked about some of the wiring. If you want to see all that, stick around. Hi, I'm David. Welcome to my channel where I like to DIY renewable energy and energy efficiency projects. This past week, I've been testing this rack of Jakiper batteries. Now, Jakiper is part of Orient Power. They sent me a pallet of 4 of these batteries. Each battery is 5.12 kilowatt hours, so the stack is about 20.5 kilowatt hours. The rack came disassembled and I had to assemble it. My daughter even helped. This is actually thicker steel than I was expecting. Looks like they have some nuts in there. And looks like this pretty good size angle. And this is just a spacer to keep the battery away from the screws. The rack was made out of thicker steel than I was expecting. The batteries come without these little wings attached. So you have to screw those wings onto the battery. And then when you slide it in, you screw it to the rack and the whole unit becomes pretty sturdy. Now there are 2 positives and 2 negative ports on each battery. Now these terminals are actually pretty beefy. They look good. The weak link is that little jumper bar in the back. I went into more detail in this jumper bar in the previous video, but just a quick rundown. Between the 2 terminals is a tin-plated brass jumper bar that goes between the 2. Now I took that out and I used a file to file off a corner of it, and it definitely looks like brass to me. It doesn't look like copper at all. So it's not going to have the same amp carrying capacity or ampacity as a copper bar would be. I'm worried it's going to get pretty hot. So I'd like to put a temperature sensor, which is right on the end of this wire. And I like to tape this right onto the jumper bar so I can get the jumper bar temperature. So I just picked the 1 second from the top here. Instead of doing either the top or bottom, I just wanted one in the middle. This will give us the temperature display in Celsius of that jumper bar. So I'm going to tape this on. I want to get the temperature sensor right in the middle of the jumper bar. So there we go, temperature sensor right there, right in the middle of the jumper bar. And it's exiting through this hole on the side. Now I'll just screw this all back together and get it into the case. I have my central bus bars and my shunt up on top of the battery. And I've got these 2 leads coming out. There's a negative and a positive. I have the 4-aught wire run all the way down to the bottom. The bus bar is now tucked in on the side. So I'm going to attach it. Right here is going to be the main positive 4-aught wire, and it's going to my bus bar, which is just on the side here. Now this is just hanging. It's not how it should be. It should be mounted, but we're just testing this out right now. And now we've got our Victron shunt and the main negative. With all the batteries in the rack, I'm ready to wire it up. I'm going to be using the wiring that Jakiper included. They sent me 3 of these envelopes. These are an additional item that don't come with the batteries when you buy them. They sell them for $15. Inside is a pair of wires. You get 1 red, 1 black. They're about 1.5 feet long with ring terminals on the end. Now, the batteries themselves come with these little rubber caps to go over the ends. So the wire doesn't come with the rubber caps, but the batteries do. So I've already slipped these over the end, so that way when I screw these onto the terminals, the rubber caps are already there. You got to do it in advance. Now there's several different ways of wiring these. Jakiper has a way which is called daisy chaining. It's not my preferred method, but I'm going to do it the way that Jakiper has kind of set this up. I will demonstrate what I consider a better method in a future video, the next one coming out. But right now, let's just hook it up the way that is recommended and see how well it works. Okay. Well, let's start off with the top here. And now I'm going to go diagonally over. And we'll just move down the line. Right now I'm just attaching these fairly loose, and then we're going to go through and tighten all of them together. I'm wiring these so the wires kind of loop down the middle of the battery. That way the circuit breaker on the left and the screen on the right I can still reach. Okay. I'm kind of holding on the side of the lug. I'm not holding the wire, I'm holding the side of the lug to prevent it from spinning. The manual that came with the batteries actually gives a torque specification for these terminals. And it says here 12 to 15 Newton meters. So I'll set this in that range. So that's not very much. 12 to 15 Newton meters. 14 right there. That's 15 Newton meters. So that is the high end of the torque specification. So all the terminals are now at 15 Newton meters, which didn't actually feel like a lot. I felt like it could have taken more, but there we go. Last thing we can do is slide these rubber covers over. And there we go, all wired up. Our main positive down here in this corner. This empty terminal is taped off. Everything goes up through the batteries and the main negative over here, and this spare terminal taped off. So we're going to be able to record everything with the Victron shunt. It looks good. Now I've already checked that all these batteries are full. Most of them are 98, 99% because I've charged them individually before putting them in the rack. But even if you don't do that, you can hook these up. They now have a current limiter in them, so if you don't balance them beforehand, you can just throw them in the rack and then balance them in the rack. So all of them are on. Okay, so I just turned on all the circuit breakers going down the line. You can see this one is being charged at 4 amps. This one is being discharged at 2 amps, 0 amps, and this one is discharging 1.5 amps. So currently, right now, these grow watt inverters are turned off, and I also turned off all the solar input. So we're not charging or discharging the batteries right now. So we have a little bit of current flowing through these batteries, and they're all about 54 volts. Now I'm going to hook up my charger, and just that one charger, which is only a 20 amp charger, that means just 5 amps per battery. So to do the first initial commissioning charge, I'll call it, we want to bring all of these up together. If we bring them all up to 58.4 volts together, then they'll move up and down together, hopefully. So I'm just attaching these alligator clips from the charger right on the terminals here and one here. Ideally, you'd have it go all the way from one end to the other, but I don't have enough of this insulation strip back to reach, so that'll be good enough. It really doesn't matter because this is going to be such low amps, and now we'll just plug this in. And it started charging. Okay, so down here, 5 amps. 4.8, 4.6, and 5.6. So all of these are receiving some amperage, and when this reaches 58.4 volts, it will stay at that voltage and then drop the current. So these will charge all the way up. They should be near 100% already. So yeah, so that one says 100%. And that one's 99.8. So this little charger shouldn't be on here very long. It'll finish up fairly quick. So oftentimes I'll get emailed from people asking me, hey, I charged up my batteries, took off the charger, and then the voltage dropped. Do I have bad batteries? Well, no, it's typical for this type of battery, this is lithium iron phosphate, that when you take away the charger, it will settle down somewhere between 53.5 and 54 volts, typically is what I see when you take away the charger. It's not a bad battery, it's just how they sit. It's perfectly fine. Do not leave chargers on float mode on lithium iron phosphate. You don't want to float them up at 58.4. If you don't have a wall charger like this and you just have a solar charger, you can do the exact same thing. Just set your parameter on your solar charge controller to 58.4 volts for the first charge, and make sure you don't have any loads on it. So bring them all up together to 58.4 volts, and then you can start using it like normal. So typically I set up my charge controllers to charge bulk to 56 volts and float at 54 volts. So the float voltage is lower than the bulk voltage. I do that on purpose. I don't want to float these at a high voltage. So the settled voltage is 54 volts, so I set the float there anyways. So they're still at 100% state of charge, but you're not stressing the battery that way. All the packs are now balanced at the top end together. We've got all our wiring done. So next we are going to zero out that Victron shunt and do a capacity test. This is the Victron app. It is connected through Bluetooth to the Victron Smart Shunt, which will measure all the power going in and out of the battery bank. So right now we're going to reset this. Our battery capacity is 400 amp hours. We're going to synchronize this at 100%. Okay. And then we're going to look at history over here. So we're going to zero this out because none of these numbers are referring to our capacity test. There we go, zeros across the board. So now we can start our capacity test. The power is on, and over here let's start our timer. So that's going to time the capacity test. We'll get a start reference of temperature. We've got 23.1 degrees Celsius, 162 watts. Okay, so everything is off except for the dryer. The dryer is going to be our load for this test. And over here, it's empty. Okay. So now with that dryer running, we've got 112 amps coming out. So 2.7 on both inverters, so that's going to be 5.4 kilowatts. And over here, we're discharging almost 5.9 kilowatts. So that means 500 watts is being consumed in the inverters, in the losses involved in going from 48 volts DC to 240 volts AC. So we know 112 amps are being discharged through these 4-aught wires. Now let's check what is happening. We've got 27.6, 27.7, 28, and 31 amps. Now let's check. We've got 27 up here on this positive, 56, 85, and 117. So that's how this wiring setup works. So this wire down here is seeing more amperage than a 4 gauge is rated for. Along with this one up here, it's seeing more amperage, and that jumper in there is seeing a ton. So that jumper wire is going to be seeing all of this 84 plus half of what the battery is discharging. So it's going to be in the 90s, maybe 100 amps even. So let's see that initial 25.8. So it is increasing. Now remember, I've got it on this jumper right here. So that's not the jumper experiencing the most amps. This jumper and this jumper are both experiencing the highest amperage. Well, I changed something. I turned off the dryer. I didn't like that the dryer was kicking on and off, on and off. So I turned on my water heater and air conditioner, and we've got 103, and now that should be much more consistent, which is what we want for a good capacity test. Oh, and let's see what the temperature is on that jumper bar. 28 Celsius. We are almost done with this test. 3 hours and 44 minutes. Up here, got 46.6 volts, 46.8 this one's registering. So far we've discharged 20.2 kilowatt hours. No, it says 5% left. Oh, I saw that just clicked on. So we have our low voltage alarm. Oh, all of them just hit that low voltage alarm all at the same time. Now I think it's going to shut off as soon as one cell hits 2.7. I did turn off one of the loads that I had, so that because we were hitting like 120 amps, so I turned off one of the loads to drop that back down, and that's because as the voltage drops, the amperage goes up. 20.3, we're doing really good. 20.48 is the mark. 20.4, we just crossed 20.4, yes! Oh, this is good. We might actually hit our mark. We're going to be really close to it. Still discharging. Oh, we have some in the 27. Yeah, so cell 14 might be the one that caused our low voltage cutoff. This one cut off. 32 amps. So this one already cut off. It's at 0 amps. Oh, and they all killed. They all died. 20.5. Oh, that is so cool. Yes. We hit 20.5 kilowatt hours. We hit our mark. That's awesome. I'm really excited to run the load test. Now this is going to be pushing this battery bank as hard as we possibly can. I have 2 grow-out inverters behind me. Each is 5,000 watts. That means total we'll be able to pull over 200 amps out of the battery bank and supply 10 kilowatts to the load. We're going to run that for an entire hour and see just how hot this system gets. That's pretty much pushing this to worst case scenario. Now the Victron shunt is right here inside. It is corresponding to the app on this phone. This state of charge is not reading accurately right now because it got reset when all the BMSs shut off, and the Victron shunt lost its power. We're going to start this test. There we go. And let's find out what that jumper is. It's at 24.6 degrees Celsius. Now that wire comes down to this jumper, so it's reading a midpoint. It's not the worst case scenario. The jumper bar in here will get the hottest, corresponding with the jumper bar over here on the positive. But the ones in the middle of the pack don't get as hot. But these wires will. So everything is turned on down the line. So right now we're all reading the same and we're all discharging about the same. Okay, let's start turning on some things. We're going to turn on the water heater. And that kicked us up to 41%. Out of 10,000 watts, that means about 4 kilowatts. So we've got our water heater on. We're going to try turning on the dryer. And right now it's seeing 95%. And down here, almost 200 amps. It looks like that has already climbed in just 3 minutes. With this at 92%, that means we have about 800 watts left that we could turn on. Now this is a 250 watt heater. This has two settings, 750 watts on low and 1500 watts on high. Let me try the 750 watts and see if... So I just switched it to low. There we go, we've got 99%. That's awesome. So that's going to be about 9,900 watts, 9.9 kilowatts. Down here, we're pulling 10,700 watts or over 200 amps. Oh, and that jumper bar is really climbing. Here's a multimeter that I have set to DC amps. We're getting about 220 amps on the top wire, but then coming down on the negative, 168, 113, 58, and then the main positive, 220, 162, 107, and 52. As you can see, some of these are going to get hot. This one's already getting pretty hot. Let me try to capture the temperature on here. There we go, 100 degrees Fahrenheit already, or 38 degrees Celsius. And the jumper bar is at 36 Celsius on this one. Remember, this jumper bar is going to be carrying even more amps and getting hotter. And we're only 7 minutes into this test. All right, let's check our temperature. Cells are doing fine, but already we're warming up inside. Yeah, that jumper bar is really getting hot. Oh, and this one's bouncing around 100%. There we go, 100. All right, half-hour update. Right now the heating element in the dryer is off, but let's watch as that kicks on. When it kicks on, it jumps up to 102%. There we go, 102%. Yes. All right, at 31 minutes, let's see how we're doing. 213 amps, 46.6 degrees Celsius on that jumper. Discharging 52 amps. The cells are doing fine. As you can see, the PCB is getting hotter. And let's check our amperage on this top wire. 168 amps DC. Oh, and that heating element shut off. I don't like this wire for carrying basically these bottom 3 batteries all have to transfer their power through this one wire. All 4 batteries will transfer through this one. Likewise, the top 3 transfer all their power through this positive wire, and then all 4 come out the bottom. Well, we are 1 hour into the test. The heater on the dryer is turning off, and I'm seeing that it's actually been turning off for longer periods of time. So I guess the temperature inside the dryer must be pretty high. Just went up to 100. All right. So we've got 214 amps, 48 degrees Celsius on that middle brass jumper bar. And let's check out the temperature here. Got 125 Fahrenheit or 51.8 Celsius, and should be similar down here. 59 Celsius or 138 Fahrenheit. And let's see what our temperature inside is. Oh, went past it. Yeah, there we go. But they kept running, but this is just, that's hot. Okay, so I don't like daisy chaining them like this. They get too hot. But they are handling it, and nothing has exploded or fallen apart. Well, that concludes a pretty hard load test. As you saw, we were pulling about 10 kilowatts for an hour out of this battery bank. Now, when you daisy chain the batteries, that means that the amperage really has to flow through a lot of these connections. So even if we had thick gauge wire, it still has to flow through the connections and through those brass jumper bars. This is not the best design in daisy chaining batteries. I really want to see a different design, which I'll get into in the next video. Now, we saw that jumper bar get up to 49 degrees Celsius, and we even saw the 4 gauge wire get up to 59 degrees Celsius. Now, that was too hot for me to hold my hand on it. I could just briefly touch that wire, but I did not want to hold it. The thing is that even though the jacket of the wire says 200 degrees Celsius, so we could say, hey, we're not at risk of the wire catching on fire, that is still not the ideal way of designing a battery bank. All of that heat loss is energy loss. We put in tons of effort into making the solar array outside and running the wires in, and it takes years of saving and planning to build these types of systems. Why would I want to lose all the energy to the surrounding environment in the form of heat loss? Electronics that run cool are going to run more efficiently, less energy loss, and that just makes the overall system a better value for the money and effort that you're putting into building it. Now, the 4 gauge wire on the very top and the very bottom, we saw 167 amps. Now, that's almost double what the NEC allows. So this type of setup would not pass code. On a positive note, we didn't have the batteries fail. They didn't shut down on us. So in that regards, the load test was a success from the point of view of the batteries, the cells, the BMS. They all handled it. So I don't think that the batteries themselves are bad. And I'm thrilled that we actually hit 20.5 kilowatt hours out of the battery pack. When we ran the capacity test, we did hit 20.5 kilowatt hours, and that means we hit our spec, which was 20.48 kilowatt hours for the pack as a whole. So I'm actually really impressed that the entire battery bank hit its spec in that regards. And when we did our load test, none of the batteries actually shut down, none of the BMSs failed. So again, I'd say that was a success. The failure is in the design of daisy chaining these batteries together. Thank you everybody so much for watching. If you enjoy these videos, please like, subscribe, comment, share. Check out the links in the description below for a discount code to buy some of these batteries if they will suit your needs. Thanks everybody.